So I was scrambling for video ideas, but then I had a thought. What if I just asked ChatGPT? So I'm gonna ask ChatGPT to make me a video idea. Okay. Day in the life. A how-to video. A reacting video. I think I actually like the how-to video a lot, so I'm gonna make a how-to video on how about a convolutional network. Yeah, let's do that. For the IDE, we'll be using Cider Cloud, which is a developmental server made for machine learning. It has a generous free tier, so if you want to get started with it, you can click the link in the description. So once you're on this page, we're gonna click a new server. We're gonna give it a name, GPU, and this should be more than plenty. We're going to set this to not PyTorch, we're going to set it to TensorFlow, and we're going to, that should be more than, if you want to add a Git repository, you have it here, and you can press create. I've already made one, so same thing, so we're just going to start it. Yep. Okay, so it looks like the IDE has been started, so we're just going to click on this button here, and that is going to open up our workspace. So let me go out of dark mode here. So you can go to terminal. You can open up a new notebook, which I already done here. And yeah, so you just click this and give it a name. You can also connect to a Git, look at the resources, and install extensions. Okay, first things first, we're gonna set this to dark mode, go to theme, super light dark, and let's get started. So we're gonna import what we need. We're gonna import numpy as MP and import tensorflow as TF. So we're gonna press run, and looks like it worked. Okay, so let's get started with the data importing. So let's do data. So to get the data, all you need to do is you can import it from tensorflow.tras.datasets, and you're going to be importing the MNIST data, and we're going to set it to raw. So this will have a list, and in the list there will be two lists, and the first one is an image, which is a 2D array. So we're gonna have image, or it'll be the train image. You also have the train labels. I'm just gonna shorten a bit. Then you have the test images, and you have the test labels. Oops, you're gonna have raw, and you need to load the data, so load data. Here we go. So let's test it out. Perfect, it works. Okay, so next up, we're gonna import matplotlib. So import matplotlib.pyplot as plot. Now this is gonna make us see the picture, so we're just gonna do image show, and we're gonna take a train image, take one of them, the first one, and we're just gonna call that. Oh, we're gonna import this first, and we're gonna call this. Something you can do is set the color map to gray. Or I think it might be grays. Is it spelled differently? Oh, the capital is, yeah, the G is a capital. There we go, and that makes a black and white image. After that, what we're gonna do is, after we get the image done, we're gonna make it smaller. So test or train images, we're gonna set that to itself, but we're gonna limit it to, let's say, 500 images. Same thing for the labels, so I'm just gonna be, and yeah, so we will have 500 images and 500 labels, and that will make building the model, prototyping it easier. Okay, so now we're gonna make the data more refined. Essentially, we're just taking the data and making it more usable for our model. So first things we're gonna do is we're gonna take the images and we're gonna give it another dimension. So train images dot reshape. We're gonna set this to the first value of the shape, which is essentially how many images there are. So in this case, it'll be 500. We're going to set 28 by 28 because that's the size of the image, and by 1. Next, we're going to change the type to a float 32. After that, what we're going to do is we're going to divide each shape, because right now it is from 0 to 255, but we want it to be from 0 to 1. So essentially we're just going to do a mass divide by 255, and this works because we're using numpy instead of regular lists for our images. So let's test it out. We're going to add a cell above by right clicking, and how do we add? I think you gotta press this one actually, yeah. So we're gonna take the shape of this before we do the transformation. This will be 528, 28. After we do it, oops, got a comma there. After we do this, we're just gonna set the shape again, and we'll see we have another dimension. Okay, next up, we're gonna be working on the model. So let's open a new cell. We're going to be importing tensorflow keras as keras, and we're going to be importing tensorflow.models, just one, from tensorflow .models import sequential. And we're going to do the same thing, but for layers. For the layers, we're going to need a bit more than this, but for right now, we just need dense, we just need flat. So let's build a basic model. So Keras uses a very basic sequential feature, which is, or it's like a model layout where you add layers one by one, and that is the neural network model. So let's make a very basic model. We're going to start a sequential, and to this model we're going to add a flatten layer first. What the flatten layer does is it essentially takes an image, which is 28 by 28, a two-dimensional image, and make it one-dimensional. So this is going to multiply those two, and that's going to be the size of it. Then we're going to add a dense, and the dense will be 10. 10 will be the output of it. So since we have the labels will range from 0 to 9, which is 10, possible outputs, we have 10 as output. And yeah, this is a working model. You can compile it. You can do the model.compile. You do need an optimizer, so we're going to set this to Atom, and I believe that is it. And you can also evaluate by using the test images and the test labels. So if we run this, you can see that it has infinitely 0, so not the best so far. I think that's because we didn't add a what do we not add? A loss. We didn't add a loss function, so we could just do mean square error, which is not the right one, but yeah, so we just, yeah, this wouldn't be a good model per se. Luckily, however, I'm not here to teach you how to make a bad model. I'm here to teach you make a working one. So we're gonna fix this up and make this actually see the shape. So let's see. What we can do is we can add a convolutional network So I think it is com2d. Yep, and we're gonna add a max pooling, and we're gonna add a dropout. So first of all, we're gonna add a convolution network. This is what makes the model work. It is essentially the best ideology I heard is like it's a spreadsheet. So you see how it's like a spreadsheet, there's cells around it. So it searches for patterns within the spreadsheet, which is the image. And based on certain patterns, like for example, a 1 might have a line and maybe a couple like horizontal lines on the top and bottom and a vertical line in the middle. That will be a 1. An 8 will have like 2 circles. So it'll search for those patterns and guide them towards the right digit. So let's add the convolutional neural network 2D. And we're going to give it a size, which I'll say 64. That seems to be working. And we're going to set the kernel size. And this is the size of the pattern match. Since it's 20 by 28, I think either 4 or 5 works. So I'm going to set it to 4 and see how that goes. Input shape, it is going to be the shape of the input, which as we already seen is 28, 28, and 1. So there is that. Did I miss something? Oh yes, I did. Okay. Next up is max pooling. Now what max pooling does is it's there to help reduce overfitting and also help performance. It essentially takes a chunk of area and takes the largest pattern from it. So it won't look at all of the patterns, it will just look at the most prominent ones. So we're going to add a max pooling. It's actually 2D. Since it's convolutional 2D, and we're going to set the pool size, which is similar to the kernel size, but you know, we're going to make it just a tiny bit. So this should help both overfitting and performance. Then we're going to add the flatten phase, and this is where we'll begin the learning neural network. So this essentially makes it easier for the dense model to function, since what this does is it just gives us patterns. It doesn't give us individual pixels. So this will make the model learn way faster. So we're going to add a master dense model. We only need 1 layer for this. If you want, you can experiment with several layers. I find that 1 layer is more than enough because this is not a heavy data set. So we're going to set this to sigmoid or ReLU. I actually prefer ReLU because it's more efficient, but it shouldn't matter. I'm going to set this to dropout, which will also reduce overfitting, and this. So we want the output to be 1-hot encoded. So to do this, what you need to do is you need to set the activation to a softmax. And what this would do is it'll give a list of 0 to 10, with each index being a probability. And what we do is we just take the maximum probability, and that's how you get the answer. So we're going to see if that works. Kernel size is not defined. Maybe I spelled it wrong. Did I spell it wrong? Well, I forgot an equal sign. That might work. Pool size is not defined. Same thing. And that seems to be working. So we're going to compile the model and test it. Well, the loss, we're not actually supposed to use MSE or mean square error. We're supposed to use something called sparse categorical cross entropy. That is a mouthful to say, but essentially this is a categorical problem or a multi-class problem because we have multiple classes or digits and we'll try to filter between 1 or 2 of them. So we'll be using this one, which is optimized for that specific case. And you can see our loss being significantly lower. Well, the reason why this is so high is because we have a model, but we haven't trained it yet. So let's try training it. What you need to do is we just gotta fit and we need to set the training data. So the data for the X, it will be the training images, and for the Y, it'll simply be the training labels. So we're going to set the epoch or epoch, however you like to say it, to, let's say 5. And we're going to see how that goes. Oops. There's an S in there. And must contain the number of samples. I don't think I forgot. Yeah, I forgot to put the labels of it. So we're going to run this. Now get us the labels. Training image is not defined. Got the S. There we go. And since this is a new one, we need to redefine all of the data filtering. Then we're gonna do a new model just to be safe. We're gonna try running this. It runs very quickly, and you can see the loss going down significantly after each epoch. So we're gonna evaluate it one more time. See if that goes. Well, would you look at that? It actually went up a bit. So let's try training it a little bit more. And yeah, so we have a classic case of overfitting where the data for the training data is like, it works very well, but for generalization, so for other data, which is the test data, it doesn't work. So good ways to solve overfitting is by first using more dropouts. So we have it at set to 0.2. What if we increase it by 0.3? Now you don't want to overdo this, because if you overdo it, then you're going to have more problems later on. But let's just increase it just a tiny bit, see how that goes. You can see that the evaluate for the test is high and for the train is low, so we still have the overfitting. Next up, we could make the ReLU into a sigmoid. This is going to cost more resources, but hopefully it should reduce overfitting. Now it does actually seem to reduce it a bit. Let's give it a couple more epochs. And yeah, so that does seem to reduce overfitting. However, the range between the test and the train is still kind of high. What we're actually going to do is we're going to add a metric. Metrics equals. Let's see. I think I spelled that wrong. Accuracy. There's no R in there. Okay. So what this would do is it'll give us an accuracy metric along with the loss. So we're going to use this, and you can see that there's still a discrepancy. So another way of combating overfitting is more pooling and a slightly higher kernel. See if that works. Right now it's at 82. 50, so actually does not seem to work. And it's important to just play around with this, you know. So I'm gonna drop this down. I think the ReLU and sigmoid is important because sigmoid seems to do the most at this so far. And yeah, so we're back to where another thing you can do is just make the data set a bit larger. So we had it at 500, we're gonna triple it. And there's not much we're going to do to the data, we're just going to make it larger. So now you can see the accuracy is going to 98%. For the test data, it jumped up to 90. So there's still a discrepancy, but it's getting closer and closer. Finally, when you feel like you have made significant changes to the model and you feel like that the model is in itself good enough to train, you're going to start the full-on training. So we're not going to be limiting the data, we're just going to be having all the data. So let's start it. Now we have 60,000 points of data, or 60,000 images. We're going to remake the model, and you can see or actually it's very little because we haven't trained it yet. We're going to train it for a bit, and this is going to take a while. Now, since Saturn Cloud has a GPU, this is going to take faster than if you were to run it on your machine, unless you already have a GPU on your machine. Unfortunately, I have an AMD which doesn't support TensorFlow on Windows just yet, without WSL or just installing Linux. So I'm just using a cloud provider. You can also use Google Cloud or Google Colab, which is also great for a free GPU. They even have TPUs over there, so if you want to do a lot of word processing, that's a place to be. Okay, we have a very good accuracy at 99. We're going to test for overfitting, and it's good enough, I think. It's a little bit lower than last time, but that's mostly because of the large amounts of data. But I think this is more than reasonable. So once you're done with your model, what we're going to do is we're going to test it out. So let's get image. We're going to set this to test images. We're going to set it to a random number and label test labels. Same thing. Make sure these are the same numbers, otherwise it may not work. Then we're going to get a we're actually going to show this first. So plot.image show, and we're going to put the image, we're going to set the CMAP to grays. Oops. Show this, you have this, and you can obviously, this is a 1, and you can also say this is a 1 by just using the title function. So we can say actual, and not that, actual, and you can do lab. Concatenate string. Did I not put this to string? Okay, so string of the label. There we go. So actual 1. And let's see. You can also predict it. So this is the big part. In order to predict something, what you need to do is you need to take the model, predict, and you'll be predicting the same data format as the input. So since the inputs and outputs are basically the same, we can just put that in, but you did need to be aware of one thing, which is that we did a data refinement right over here to the the train images, but not the test images. So essentially we're going to do the same thing over here, but to the test images. Gotta run this. There we go. So now, if we predict a test image, which will be here, we'll get a result. Well, let me see. Oh yes, since it needs to be exactly the same. If we have this, let me get a new one to show you. So if we take the shape of this, you can see that the shape is 10,000, 28, 28, 1. But if we take the first one, we take the shape of this, it's only 3 dimensionals. So I need to reshape this. Reshape this to 1, 28, 28, 1. It's a little weird, but that's how it goes. So now after that, we have this array. Now this might seem like jargon, but essentially you're just looking for the highest number. And it seems like they think that is a 2, because it's in that. So a good way of doing that is just using the argmax. So we're going to be taking the prediction, we're going to be doing argmax, and give you the index of what you thinks. Oh, it's a 1. I forgot to count from 0. Oops. Yeah, so you take the argmax, it will give you the index of the maximum value, which is a 1. Now we can combine this. So we're going to do plot.image show, and we're gonna take the image and we're gonna make sure we CMap it to grays. You don't need to do this, it's just visual and I like doing this. So we're gonna have that. We're also gonna print. We're gonna print actual, and we're gonna set this to a string of the label. And same thing, but this time will be the prediction, and it will be the string of this argument right here. So if we run this, it has no image show, well that's because there's no G in there. If we run this, you see that actual and prediction is 1, and this is the image. Let's do another one. Let's actually import random. So we're going to do index equals random dot and int. We're going to set it to 1 to 10,000 because that is the range. And we're going to set this to the index. So we have this, which is 7. If we run it again, a 9. Run it again. That's a 1. Another 1. That's a 7. That's a tricky one. That's a 2. You can see this model works very well. And to be clear, we're using test images. So these are images that the model has never touched. They haven't even seen. All it does is it evaluates, and that doesn't get imported back to the model. So there we have it. We have a working machine learning model that recognizes digits that's built on the MNIST dataset. If you have any questions, I know this is a pretty confusing topic, I'll leave them in the comments and I'll try to answer them as much as I can. Alright, thanks for watching.